Okay, continue where we left. So we gave you a general architecture of fuzzy sets, fuzzy logic, and fuzzy membership functions. And also we gave you an example of different sets of fuzzy membership functions that could be used in different ways. And we also mentioned that you can use machine learning or artificial neural networks to be able to drive membership functions. And also you can use membership function, artificial neural networks to be able to optimize the values of the parameters of these membership functions. But there is another aspect of the fuzzy logic. This is where different operations, fuzzy union, intersection, and complement. This is different to Boolean logic. Let's try to describe this because this is also linked to membership functions. So fuzzy logic begins by borrowing notations from the crisp logic or Boolean logic. So in our extension of crisp set theory to fuzzy set theory, our extension of crisp logic to fuzzy logic is made by replacing membership functions of crisp logic with fuzzy membership functions. In fuzzy logic, intersection, union, and complement are defined in terms of their membership functions along with their, of course, membership values. This section of that lecture or course concentrates on providing enough of the theoretical base for us to be able to implement computer systems that use fuzzy logic. And then fuzzy intersection and union correspond to AND and OR operations in the classic fuzzy logic respectively. And these two operators will become important because they are the building blocks for computing with fuzzy if-then rules. Because when you start combining all these different parameters, different membership functions, and terminology using fuzzy if-then rules, these intersection and union will be used to combine these. Okay, let's recap. I'm sure most of you are familiar with the crisp logic or Boolean logic, and on all operations. So if you look at the Boolean logic and operation, all the values need to be 1 so that the outcome of 1 otherwise is 0. So any value that may have 0 will yield 0. So this is where we are looking at intersection. So we are looking at everything is the same. Whereas if you look at OR, so except for this one with 2 zeros, the rest is 1. So only 1 is enough to be able to get the output 1. So union is calculated using T-norms. These are different terminologies used in the fuzzy logic literature. And T conorms operators is a function of S, and the feature is described as this with a boundary, monotonicity, commutativity, and associativity. So it exchanges between them. So the most commonly used method for fuzzy union is to take the maximum of the values. For example, you have two different fuzzy sets, fuzzy set A and fuzzy set B, with a degree of membership of mu AX for fuzzy set A, mu BX for fuzzy set B. And in order to apply OR, you need to take the maximum value. Whichever one is the maximum will get you. This is very common here because you are going to take the maximum. 0 and 1, the maximum is 1. 1, 0 is the maximum 1. 1, 1, the maximum 1. So if you look at 0, 0, the maximum is 0. So it's described that way. Fuzzy intersection is calculated using T-norms and described in that way with all the features. So the most commonly adapted T-norm or the most commonly adapted approach to take fuzzy intersection is to take the minimum. So as we said in the earlier example, so given two fuzzy sets, fuzzy set A and fuzzy set B, and they have their own membership degrees or even membership functions. It doesn't matter here. So fuzzy membership functions mu ax for fuzzy set B and mu bx for fuzzy set B, you take the minimum and this will give you the intersection. So it's very similar to this one. So if you take the minimum, all of these 0, unless this one, because the minimum is 1 here. And fuzzy complement is like a NOT operator. So you take the inverse, a kind of, and donate it in that way. So, and then you can calculate that way, 1 minus mu ax, 1 minus a degree of membership, and you can define it that way. But intersection and union are mainly use fuzzy operators in fuzzy logic. So let's give you some numerical examples and how it could be applied. So suppose we have the following discrete fuzzy sets. So, and with 4 numbers, it means that we have 2 fuzzy sets, and each one of which has these members, 1, 2, 3, and 4, and each one of these has a different degree of membership. For example, 1 as a member belongs to fuzzy set A with a degree of membership of not 4, and the same belongs to fuzzy set B with degree of membership of 3. And if you read this way, number 4 belongs to fuzzy set A with a degree of membership of not 8, and the same belongs to fuzzy set B with a degree of membership of 0.1. So let's have a look at the union, intersection, and complement. So complement is only applied to one fuzzy set, whereas union, intersection, they need 2 or more different fuzzy sets. So union of the fuzzy set N and B is where you need to take the maximum. So look at this one, maximum is 0.4, 0.4 here, 0.65 for the second one, 2, 0.7 for 3, and 0.8 for number 4. For intersection, you need to take the minimum. So it means that 0.3 for 1, 0.6 for 2, 0.43, and 0.1 for 4. And then if you take the complement of the fuzzy set A, so you need to take 1 minus degree of membership. So 1 minus 0.4 is 0.6. 1 minus 0.6 is 0.4. Here we go. 1 minus 0.7, 0.3. 1 minus 0.8 is 0.2. Here we go. This is the case. And you could do the same for fuzzy set B. If you take the complement is 0.7 here for the 1, 0.35 for 2, 0.6 for 3, and 0.9 is for 4. And how would you be able to show it graphically in a discrete form? Here we go. This is the case. Fuzzy set A and fuzzy set B, you have these members, and with the degree of degrees of membership here. So you can show this graphically here. Okay, and this is another way of graphical representation of fuzzy operations, but this time it's continuous membership function rather than discrete ones. So let's give an example. Let's say consider the fuzzy set A damping ratio X considerably larger than 0.5, and there is another fuzzy set B damping ratio of X approximately equal to 0.77, 7.707. So the damping ratio is a positive real number, and this is it has a value between 0 and 1. So consequently, you can represent fuzzy set and B in this way, and then you can formulate it, put in an equation that way. So this is the membership function for fuzzy set A. So it means that what we said here, damping ratio X considerably larger than 0.5. It means that up to 0.5 is 0, and between 0.5 and 1, it can be described that way. And for the membership function for the fuzzy set B, it can be described that way. So how you can put this into context, and you can say this is the fuzzy sets and a union and intersection and so on. This is for the continuous membership function. So this example demonstrated for fuzzy sets. So now you can see that how you can define it. And one of the ways to describe the difference between crisp set and fuzzy set theory is to explain that these two laws do not hold in fuzzy set theory. And actually, there is always something if you look at the fuzzy sets and union and intersection. So there are other ways of combining fuzzy sets, for example, compensatory fuzzy systems. And this is where you can combine in a different way. It's more mathematical, more complex ways. But it is stick to this simple terminology at the moment. Okay, now we talk about different terminologies, different architectures for fuzzy logic. And also we gave you different examples of membership functions, but how would you be able to determine membership functions? So exemplification. So there are different ways. The first one is exemplification. We use a membership function from a number of samples. So you may be able to ask different people and get their opinion. So this is a kind of discussion with an expert or group of experts. It's like a surveying, it's like a interviewing and questionnaire and so on. And for example, you can go and ask people degree of let's say temperature, degree of 40. Do you think it is hot or cold? And depending on the number of responses, you can do that way. So direct rating represents randomly selected members of the fuzzy set where some measure is available for that number. So you may be able to pick up, oh, I can say that, okay, 40 degrees may be 0.5 for all the groups. Yeah, 2 groups. Polling a number of experts involved. So for example, do you agree that 5-hour study a day is enough to get a good mark? And what you can see, the ratio of yes responses to all responses, it gives you, it may give you a degree of membership. Then you can complete for every number, every question. You can have a discrete membership functions. But the other thing is that you can use, for example, a clustering method to determine the membership function. So you have one sample and you have 2 clusters. You can find the distance, Euclidean distance, from that you will be able to derive a degree of membership. So this is how you can do. For example, now you have the data and you use clustering method to cluster the data. Now you have 3 different clusters. Each cluster refers to a membership fuzzy set, and you can use membership functions to model this. So here we go. For example, and these are also overlapped. If you use, for example, let's use a triangular membership. Even you can use Gaussian membership function because there's a center here, and this width will be able to help you to define the width in that Gaussian membership function. But let's stick to triangular membership function. So the center is the center of the triangular membership function where the degree of membership is 1. The reason is that the center here is right in the middle. It means that it belongs to that group most. Therefore, let's use it as 1. When you go away from the center, so this is more scattered, and degree of belonging is getting lower because you are going far away from the main point, the center. And if you look at the edges here, so they also set the lower and upper boundaries of that triangular membership function. You see this one here, lower boundary, and this one is the upper boundary for that. So it means that this cluster is represented by this triangular membership function. This is a fuzzy set A, and this is the fuzzy set A's the membership function. Again, for B, similarly, lower boundary and upper boundary represented by this membership function. This is the center where the degree of membership is 1. And again, the cluster C represented by membership function, this membership function, lower boundaries and upper boundaries. And again, you can see the overlaps here. So basically, there is no cluster, there is no crisp. Everything is represented in this way nicely with an overlap representing the uncertainty as well. And also you can use Gaussian membership function. So this is the X and Y and also each membership function. For example, here we go, A and B and C, you can see that A and C and CB overlapped. So you can see that A and C overlapped and B and C overlapped here. And then how would you be able to turn this into a rule base? Now, this is where we are. Now, we started talking about fuzzy sets. We talk about the membership functions. We said every member of a fuzzy set belongs to each group with different degrees of membership. And now we also talk about fuzzy union and fuzzy intersection and an OR, and how this is what we are going to use to combine all these together. Now we come to the stage where now we can use all this to come up with rules. So it means that if the value of X belongs or represented by this membership function and membership function, then this belongs to cluster A, and we can name it as 1 here, and because there are 3 different clusters here, and again B and then C here. But this is how you can define it with the if and then rules. So the second one is if X has this membership function and then Y this one and then this one. So in that case, how you can construct if and then rules that way. So, but clustering, so there's hundreds of different clustering methods. You can pick up one and you can use an optimization methods like genetic algorithms to be able to make it better and optimized. There is another question here. I'm not quite sure while we are talking about if it may have come to your mind. So I showed you 3 different clusters and 3 different membership functions, and also I showed you 3 different rules. But how many rules, how many membership functions that will be better? So actually, this is very much arbitrary. But if you look at the number of membership functions for each rule, should be equal to or less than number of parameters variables here. So this is very much used. But number of rules, no established method, but you will be able to use different ways of arranging this to establish the optimal number of rules. And also you can go, while you are training the system, the system may be able to look at to see which rules are becoming redundant because it may not be contributing towards the output. Therefore, you can get rid of these rules or even get rid of these membership functions. So it depends on different rules, but there are several studies where different methods, for example, singular value decomposition used to identify which rules may be redundant or which rules may be better, and so on. So having said this, I think this gives us a general framework to be able to define and construct a fuzzy system for decision making. So now this part is very much fuzzification. So a value comes in like a temperature or age or something like this, and then you use fuzzy sets described by membership functions. So the value is now becoming a degree between 0 and 1, like a fuzzified degree in the rule, and you are bringing all these rules together in one way or another, and then now the output of this fuzzy composition is still fuzzy, and it needs to be defuzzified to translate into real world number. For example, I want to cook something, and up to which degree. Yeah, so you put all the values, and here it is still fuzzy, and you need to defuzify the number to be able to get something that is usable in the real life. So this methodology is called defuzzifier. Fuzzy composition and defuzzifier have different methodologies. So now we explained you the fuzzification. So and now we will need to look at the fuzzy composition and defuzzifier. There are two methods generally used in the fuzzy logic applications, and these are called fuzzy models. So Mamdani is one of them, and this is very much used right at the beginning, minimum, and then you take the maximum, and you will get this membership function shape, and the specification is going to calculate the center of that shape. Yeah. So for example, if x is a1 and y is b1, then z is c1. So both inputs and outputs are defined using membership functions. For the sake of simplicity, we used a triangular membership function here. So initial stage and this means that we use minimum. So okay, x a1 and y b1, because and here you need to take the minimum. Yeah. And then the second rule is x a2 y b2, you take the minimum here. Now you complete that part. Now you need to operate the dem part of this. Dem part is processed that way. So the minimum here for the first rule, the minimum here for the second rule. Now you need to take the maximum here to get this shape, and then the fuzzification is the calculation of the center here. The second model is Takagi-Sugano model for two rules. Again, this is an example. Up to here, the same. If you look at if x is a1, this one, and y is this one, and you need to take the minimum. So you completed the process here. And for the second rule, this value and this value, take the minimum and you'll get it. So the second part is defined by a linear equation in Takagi-Sugano model instead of membership function that was the case in Mamdani model here. Yeah. So this is only membership function in Mamdani model, but the output, or it is called consequent part of the fuzzy model, this is represented by linear membership function. And you just need to take the weighted average of this. The weight comes from the this part before the then part, because you are taking the minimum. So this is the difference between two models, but these are the two models that have been widely used in the applications. Now you have fuzzified here, and then compose the system here, fuzzy composition. Now defuzzification. So without the defuzzification phase, the final output of the fuzzy system is still fuzzy set. And defuzzification is to obtain a crisp output from the fuzzy inferencing system. Actually, defuzzification, the fuzzified number is the one that you can use in real life. For example, you want to increase the speed of the card. Until defuzzification, you wouldn't know what speed you are going to apply. As soon as this is defuzzified, you will know which speed that you are going to apply to the card. And there are different methods for defuzzification. So the center of area, the minimum, maximum, bisector of area, smallest of maximum, largest of maximum. So these are the 5 main defuzzification methods used in this term. But the main one, the center of area. So for example, this is the center of area, and the center again, because you are taking the weighted average of this. So this is very much used, but the others also can be used. But if you have a way of putting this in the computational term and trying everything, you will be able to see which method may be better in your applications. So let's give you an example how this works. Let's say like based on the salary and period of employment that you have, I will be able to calculate your mortgage. This is just a make-up example. It doesn't apply to the real life. So I just want to make it up for you to see the way it's being calculated. Let's say come up with 2 different rules. Let's say the first rule, if salary is low and period of employment is low, then the mortgage is low. The second rule, I just come up with 2 simple rules, very obvious ones for you to understand. If salary is high and the period of employment is high, then mortgage is high. Yeah. So, but what I need to do here is to find membership functions to represent these terminologies: low for salaries, high for salary, and period of employment, and then mortgage and so on. Okay, now I've come up with this one, and this represents low salary, yeah, and this represents high salary, and this represents shorter period of employment, and this represents longer period of employment, and these are fixed mortgage for the output, consequent part. And then I fix these. I could have used a membership function, but you may not be able to understand this because it takes a lot of calculations. And instead, I used one value here. It's very similar to Takagi-Sugane model, where I just made x's and y 0, but I just use one single value. So like, again, this is going to be a weighted average. Okay, let's say I got a customer who earns 30K per year, and that person has been in the employment for the 15 years. So 30K, of course, that person has 2 membership degrees, because it belongs to both groups, but with different degrees of membership. So that person belongs to the low salary group with a degree of membership of 1, and that person belongs to high salary group with a degree of membership of 0.1, is understandably. Different degrees of membership. And again, for 15 years of employment, that person belongs to the low group with degree of membership of 0.5, and the other group with a degree of membership of 0.12. And again, the way you calculate, how was it? So in the first case, you take the minimum, now 0.5, you take the minimum 0.1. Then the weighted average, you need to multiply this by 50K and multiply by this 150K and divide it by the sum of the minimum 0.5 and 1, and you will see that that person could get just under 60K mortgage. So this is the simplest way of making the calculation for such fuzzy systems. You can expand this in different ways, and you can apply this using an equation here. If you are using Tagaki-Sugane model, if you use Mamdani model, you can, of course, this could be a kind of a membership function. For example, you can put a triangle membership function here, here with a bit of overlap, and you will see the difference. The only thing that for Mamdani model, you need a computational power to be able to calculate the center of that figure, because calculation the center of a figure takes time. Whereas Tagaki-Sugane model is a bit straightforward, just a simple calculation. You can do it by hand, and you can expand this example in different ways. You can have different membership functions here. Maybe you can see that I use a different membership function here, half trapezoidal, to describe this. But the more rules that you can feed in, the more terminology that you can feed in, this could be expanded. For example, if we have only 2 if-then rules here, so it may be 4, 5, 6, even hundreds of if-then rules here, and you need to compose this. So you can see that this part up to here is a composition, and then you merge all these rules together, and this part is defuzzification. As you can see, up to here, there is no value about your mortgage rate. Once you defuzzify it, now you can see a defuzzified value which is used in the normal life. So the agency, when you go to bank, it would be able to say, okay, I made your calculation and you could be offered 59.52K mortgage. But what you can do, you can change these and the values of this membership function or this one, depending on the threshold that has been set here. You can always get different numbers. You can, for example, you can just move this around. Let's say you can make it 60 or 70, and it may be 200. You will get different results here. And if you change it, for example, 15 years, and if you change the slope of that figure, of course, the membership value is going to be a bit higher, but it will not change until this gets higher. So you can see that the rules depend on the values and the degree of membership, and the more rules you have and the more parameters you have, this is going to be composed and you will get different results. So such examples can be expanded by including different fuzzified version, if-then rules, and so on. And what we said here is that actually these values, because you can define the upper and lower boundaries in these membership functions, you can use artificial neural network to learn the optimized values of these parameters. So I think this is something that we need to also discuss. There will be some examples behind this. Okay.